Before we start, it's probably worth pointing out that this video is not sponsored by any vendor I mention here, including Adafruit, Mouser, Jameco, Texas Instruments, or the random Chinese manufacturers of the couple of modules I use.
So this video is about my homemade 6-digit clock that I built basically as ghost focused, basically as a vehicle to show off the 1970s vintage TIL311 LED displays, which we'll get into much later, which are kind of unique and still quite nice. The clock is built into a plain old Jameco enclosure, and we'll show you what's inside. It's running off a real-time clock chip, which is a Analog Devices DS3231 temperature-controlled crystal real-time clock. We'll talk much more about the inside and how this clock was built, but I do want to show you that I have it running right next to, on my desktop, a 21st century Heathkit, as opposed to a 20th century Heathkit, a 21st century Heathkit GC1006 clock that I've heavily re-engineered. Notice it's running orange digits, not red or green, to run not off of line frequency, but also off an Analog Devices, in this case a MAX 31328, which is the successor to the DS3231. They're both essentially very similar chips. They're both real-time clocks. They're both temperature-compensated, crystal-controlled. They both have a stated accuracy of more or less around plus or minus 2 to 5 parts per million, which is something in the neighborhood of means not losing nor gaining more than about 90 seconds per year. These time bases are really nice, and they've been around forever. Although the DS32318 has been around for 2 years now. It's a successor to the DS3231. The reason I have these together is you notice they're perfectly in sync, and obviously they don't talk to each other. They're running off of independent time bases, but they've been running for, I don't know, weeks now, not drifting significantly one from the other, or for that matter from NIST time, which is how I synced them initially. These time bases are really nice, and we'll talk about those in a little bit as I get into basically this clock, which I built from scratch. We can get a close-up of the TIL311 displays by removing the front plastic and this little piece of red theatrical gel. And now if we zoom in, we'll zoom in on 4 of them. You can get a pretty good look at what the dot pattern looks like. Again, all the 7 segments are essentially this dot pattern is being just generated internally by the each TIL311 display. And so it decodes basically 4 bits of number into the digits 0 through F. Obviously I'm only using 0 through 9. However, if I do a reset, I wrote a little self-test into the code so that if I reset the clock, it actually cycles through all the possibilities 0 through F, and it also lights up all the decimal points, and you'll have noticed there's 2 decimal points, a left and a right in each display, and that's what I'm scanning back and forth.
Here's the data sheet for the Texas Instruments TIL311 display, which was last made by a company called Teos. What's interesting is the apparently this was still in production as of 2004 if you look at the bottom of the data sheet here. So, you know, some 30 years after it was in general use, I guess it was still being made. This data sheet, by the way, is off of the Mouser.com website of all places, and no, Mouser lists it, but lists it as obsolete and no longer available. So these are fairly available on eBay and elsewhere, but I don't believe they're still in active production. Anyway, so your 4-bit latch, your decoder, drives these LEDs into various patterns which create digits, which I'll show you in a minute. It's a 14-pin dip display, and what's of course nice is that the latch and decoder, you put 4 bits in, here's the chip in the middle of the digit, and it displays a digit 0 through F. What you have to be careful for is that you'll notice there are two decimal points. So there's a left-hand decimal and a right-hand decimal, and that's nice. And that's these two LEDs down here on the schematic. But notice these two LED decimal points do not go through any logic. In other words, they're driven from one of the pins, which is called LED supply, which you run up to 5 volts. You just put 5 volts here, and it comes straight down into the LEDs, and it's up to you to drive the LEDs low. And you'd better do that through a resistor, of course, because if you don't, if you just ground this pin on the display or this pin, you will very quickly burn out that decimal point. And that happened to me once, and it was a lesson learned accidentally. And I said, "So crap," because now one of my digits, not on this clock, but one of my digits doesn't have a decimal point, one of the decimal points anymore. So do remember to drive these however you want, low, but through a resistor. Apart from that, the only other thing I'll show you here is we'll scroll down a bit, and these are the digits that it generates. So they're sort of 7 segment, but they look nice because they're a little bit more stylized with extra LEDs here and there to create good looking hexadecimal digits. The only other thing I'll mention is there is a blanking input here, and I actually use this in the clock. If you drive this high, the entire digit is blanked. Not the decimal points, because those are driven separately, but the digits are simply blanked. And if you drive it low, the digit is enabled, and that's sort of binary. But this, you can, and it does specify that if you want to PWM this blanking input, you can set your intensity. And so I do take advantage of that in the clock, and I don't run the digits at full brightness. I send the blanking input a PWM to run it at maybe 70% brightness, something like that.
The displays are 14-pin dips, and they're plugged into 14-pin dip wire wrap sockets onto the perf board. Looking inside, we look at the rear panel. We have the reset switch, the time set switch, the hold toggle switch, 9-volt barrel jack, DC jack in, which feeds one of those Chinese DC buck regulators, which I've obviously set to 5 volts because that's what this project calls for. Moving to the back of the front board, we have the Arduino Pro Mini here, which is sort of my go-to processor for all the different clocks I built, and of course it runs all the firmware for the clock. The 6 LEDs displays are the TIL311s, are each mounted in their own wire wrap socket. And then finally we have this module, which is it's an Adafruit PCF 8575 chip in a breakout board. And what it does, it's an I2C port expander. So you connect it up to your SCL and SDA lines on your I2C bus, which of course the Arduino Pro Mini provides, as well as where the real-time clock module lives. And it gives you 16 possible breakouts. These are effectively open if you're using those outputs, they're effectively open collector, and then you can pull them low individually or in groups. And so I use 16 of them because there are 16 decimal points, 2 on each display, and I pull them low through dropping resistors that you can see here on each TIL311, because as we've talked about, the TIL311 decimal points are not decoded or dealt with on chip in any way. They're simply brought out, and if you pull them low, you have to pull them low through a resistor, and then they light up. If you pull them low without a resistor, they burn up. And that's really the only thing I'm using this little breakout module for, is just to give me more I/O pins to run the decimal points and make them scan.
Adafruit actually offers 2 different flavors of I2C GPIO expander breakouts. One of them is based on the chip called the MCP23017, which is extremely powerful, has all sorts of options, has all sorts of configuration registers that you get to set to make it do exactly what you want and how you want. It's a very powerful chip and quite complicated. They also offer this one here, which is the PCF 8575 chip, a base chip breakout board. And this is the one I chose to use in this application because apart from being very inexpensive, it's dirt simple to use. There are in fact no configuration registers on this chip to set. Basically, if you want to output zeros and ones, you basically write 2 bytes, 16 bits of zeros and ones to the I2C address, and bingo bango, you're done. The pins instantly assume that state. More on that in a second. On the other hand, if you want to input, you simply do a 16-bit or 2-byte read from the I2C device address of this thing, and you now have instantly the state of all 16 pins. The only thing this chip can't do is when you're outputting to a bit, it cannot source current. So what happens is if you write a 0 to a particular pin as part of the 16 bits, if you write a 0, it will bring that pin to ground or drive it low. It'll drive it low, and that's good. On the other hand, if you write a logic 1, that pin goes basically open collector, which means it will not source current, nor will it sink it to ground. It'll just float effectively, which means if you have an input and you want it to be 1, you need an external pull-up to that. In my case, that's perfectly fine because the LEDs, the 12 decimal point LEDs I'm driving with this, are driven by 5 volts to their anodes, and then I simply run their cathodes through a resistor to each of these pins. And so if I want to light up the LED, I write a logic 0, which grounds the cathode, and then the LED lights up. If I want to turn it off, I write a logic 1, which basically essentially disconnects that LED, so it turns off. So the logic is inverted, but that's okay. It's really simple to use, and that's why I chose this particular breakout with this chip. The version I got from Adafruit did not have the quick connectors here, these I2C connectors that are now popular to connect up I2C stuff together. I guess it was a slightly older rev of the board, so I simply connected to the SCL and SDA pins as you would expect for I2C. And it works extremely well, and it's again a ridiculously simple and very inexpensive chip to use.
Finally, in here we have this sort of round module which is sort of taped to the bottom. This is an analog device as DS3231 real-time clock module, which is created by a company called Macetech. It's called a Chronodot. In this case, it's a Chronodot 2.1. And I go into more of if you want to know more about these real-time clock modules, I have a separate video about them. But you might ask, why is this thing just flapping in the breeze, taped down to the bottom of the case, and then extended into the main board next to the Arduino Pro Mini here? And the answer is because originally when I laid this board out, I was intending to use these bad boys. These are if you Google DS3231 and search for it on Amazon or eBay, this is what you're going to find. These are breakout modules with battery backups, and they basically are functionally identical to the Chronodot modules, except they're dirt cheap. And so the board was originally designed so that this would plug in vertically into that connector that cable is plugging into, and it still could, because the pinouts are the same functionally. The reason I used to use these a lot because they're dirt cheap and they used to be reliable, but now recently, not that recently, but I've always gotten batches of them where I have to check them because the DS3231 chip, which is a larger chip here, I've found some fakes or counterfeits or just off-spec ones which simply don't perform functionally or even reliably or even accurately. And so I've stopped using these. Now, yes, they're cheap, And yes, the Macetech Chronodots are significantly more expensive, but my time is valuable, and I don't make that many clocks that I can't afford decent products by reputable companies using original manufacturer chips. And so that's why this Macetech Chronodot is running the show, and it has its own little battery backup built in there. And in a nutshell, that's my clock using TIL311 displays.